Okay, so we're now going to talk about something called Pascal's triangle, and we're going to approach it by looking at some of the patterns that have been established already in our expansion of binomials. So, for example, in our expansion of binomials, I want to look at the coefficients real quick. So the coefficients are in the first one. So let's say this is our starting power. We'll start with 0. Usually, like on a graph, you start at 0 on the x-axis, 0 on the y-axis. That's the origin. A lot of times we use this kind of 0 notation to say, like, this is really the beginning of our pattern. So we're going to start with 0, and our coefficient is just 1. Okay. Over here, our coefficients are 1 and 1, then 1 and 2 and 1, then 1 and 3 and 3 and 1. Okay. So we want to think about those, and we're going to think about if there's any pattern we're seeing emerge. Okay. Now, what you will get if you put those numbers together and try to kind of show a pattern here is you will get this. So, try to cover up the bottom of this. We can zoom in. All right, here we go. You will get this. So for the first one, the coefficient was 1. For the next one, we had 2 coefficients of 1, so 1 and 1. Then we had 1, 2, 1, 1, 2, 1. Then we had 1, 3, 3, 1, 1, 3, 3, 1. Okay, so not intuitive in any way why you would want to arrange them in this triangle. But what we're going to notice is that if you do, so if you, maybe lesson here is if you just play around with math, if you do it in weird ways and put it in weird combinations and just kind of get creative, then you can find really strange and interesting things kind of hidden in nature, hidden in numbers. This was first done, I believe, in China. Then, like 600 years later or so, it was done in Europe by a guy named Blaise Pascal. Blaise Pascal contributed a lot of different things to science and math. He, within kind of a Western learning tradition, bears the name Pascal's triangle. Not necessarily the first guy to ever do this, but he's the guy we credit it to in our traditions of learning. So what he did is basically I'm not sure if he came to this by way of looking at binomials, by the way, or if he was just playing around with this. I believe the story was he was just kind of a little kid at the time and he was playing around with numbers. I believe that's my understanding. It was just that this was a discovery by a child who was playing around with numbers. So basically he puts 1, and then on either side of 1 he imagines a 0. Now, if you have noticed already, the pattern, the kind of main pattern to discover here is that each number can be made out of the 2 numbers above it. Okay, 3 can be made out of 2 and 1. 2 can be made out of 1 and 1. If we imagine a 0 on the outside, then 1 and 0 make 1. That's why these continue downwards as 1s the whole way, because we're kind of imagining zeros heading out to the sides. Okay, so each number is made up of the 2 above it. Okay, so if we wanted to say what is a plus b to the 4th power, what are all the coefficients? If we continue this pattern, this is what we get. We get 1 and 3 make 4, 3 and 3 make 6, 3 and 1 make 4. Okay, so let's check to see if that's actually what we get. So if I take a plus b to the 4th power, effectively I'm going to be doing a plus b cubed times a plus b again. So I've already written out a plus b cubed. It was this guy here. So I'm going to take this and I'm going to multiply it with a plus b to the 1st power. And together that will give me, 4 iterations, 4 multiplications of that binomial. So it would be to the 4th power. Okay, so I've written this out in an area model. This is one length, that is the other length. Okay, here and here. Here and here, we get a to the 4th, 3a cubed to b, 3a squared b squared, ab cubed, a cubed b, 3a squared b cubed, 3ab cubed, and b to the 4th. Okay, I think some of those simplify together like a squared b cubed, maybe not. A cubed b. Yeah, so there's some like terms in there. So instead of 8 terms, we simplify it down to 1, 2, 3, 4, 5 terms. And what are their coefficients? Well, it's 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Okay. So for some crazy reason, and it could be a reason people understand, I don't understand it. I have no idea why it's in there. I've been trying to figure it out for the last couple of days so I could pump up this lesson with, every explanation about what the heck is going on in math. But as far as I could tell, if there are people on the internet who know why this property exists, that you can get these binomial coefficients by doing this interesting pattern, simple pattern really, I haven't found them. I haven't found anybody who's clearly and easily explained it in a way that I can process and give to you guys. So it might be known, it might not be known, it might be something for you to discover if you play around with this and you become that next kid who's playing with numbers and figuring things out. So I'm not sure. But at this point, what we do know is that this triangle is very good at finding the coefficients of those different terms when we expand a binomial. Okay, so let's look at your book real quick. Let me see if I can find it. Around here somewhere. And look at an example that's in the book, which is basically just very quickly we're going to fill in Pascal's triangle. Okay, so here we want to use Pascal's triangle to expand to x plus y to the 7th. Well, we're going to put a 1 here. 1 and 5 are going to make a 6. 5 and 10 will make a 15. 10 and 10 will make a 20. 10 and 5 will make a 15. 5 and 1 will make a 6, and then a 1 over here. Okay, for that final line, we'll just combine these two numbers. So that'd be 1 and 6 make 7. 6 and 15 make 21. 15 and 20 make 35. 20 and 15 make 35. Okay, we have symmetrical, and you can see them along the bottom. And we get 21, 7, and 1. I think these exponents didn't really get formatted well in the book, but basically we just use Pascal's triangle, and we get all of those coefficients. So we know how many ways you can make 6 x's multiply and 1 y multiply. So if you're imagining those area models, those volume models where you have the boxes, it's hard to use that in your head and say, like, what would that look like for multiplying 6 times? Because we're three-dimensional people living in a three-dimensional world, and having a 7-dimensional multiplication problem is outside of our ability to simply draw a picture of. But we do want to keep in mind that, like, this x to the 7th is the part of that diagram where you took x times x times x times x, and every time you had a choice of either multiplying by x or y in this case, you multiply by x every single time. This y to the 7th at the end is the opposite. It's where when you were given the choice to multiply by x or y, you took the branch that multiplied by y every time. Okay, so let me kind of show something that illustrates that. So what I'm saying is that if you have a plus b, so a plus b multiplied by a plus b multiplied by a plus b, it's the same thing as when we said heads or tails, heads or tails, heads or tails, and we multiplied to say, okay, heads, 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 h cubed. Well, this is a cubed. That's one of the options that you can get in this diagram. You could be the one of 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different volumes that get made, and one of them was a times a times a. There's 3 of those volumes that are a squared b, and you can get those by following the paths where you go a times b, a times b times a. Okay, as long as you have 2 a's on your path, that counts as one of those. So we have 3 of those. We have a squared b, a squared b, a squared b. We have 3 of them. We have 3 ab squareds if we follow those paths. So abb, bab is b squared, bba, 2 b's in there, so b squared a. And there's finally just one of these options. Okay, so that is what we were talking about there. We are talking about the fact that the coefficients of Pascal's triangle do a really good job of telling us how many different types of the same object are we going to find? How many a squared b's are we going to find? We're going to find 3 of them. That's what Pascal's triangle tells us. It tells us that coefficient there, the 3, the 1, and in higher dimensions where I can't continue to draw these pictures, it still tells us that. It still tells us, like, if we're just going to do a times itself 7 times, the coefficient out front is just going to be 1. If we do, looking at Pascal's triangle, if we do, so this is, I have to remind myself, so this is a to the 0, to the first, to the second, to the third, to the fourth. So if we do a to the fourth, and we want to know how many a squared b squareds are there? Well, there are 6 of them. And how many a to the first b cubes are there? Well, there's 4 of them. How many a cubed b's are there? There's 4. How many a to the 0, b to the fourth are there? Well, there's just one. There's only one way to get it. You have to go b times b times b times b. Oh, sorry, that's kind of off the page. Okay, over here would be a to the fourth, b to the 0. Okay, it's telling us how many of these products that we're going to get. Okay, that's what Pascal's triangle can do. It can get to those answers for us. So, separate question is there any way that we can get to these numbers without actually just drawing the whole triangle? So, for example, if I wanted to do a plus b to the 100th power, do I actually have to make 100 rows and do all the addition? Or is there a different way to do that? Okay, let's put that back into like real world situations. If I wanted to say I'm going to do 30 heads or tails flips, and I want to know how likely is it to get 20 of them to be heads, do I need to make 30 rows of a Pascal's triangle and then look on row 30 and search for it? Well, you don't. And there's a technique to know how to do it. And it really has to do with this idea of combinations. Like, how many ways can you combine 3 A's and a B? Well, there's 4 ways to do it. How many ways can you combine 2 A's and 2 B's? Well, it turns out there's 6 different ways to do it. Okay. And we'll get into that in the next video, the topic of combinations. But keeping in mind, what we're really looking for is we're looking for ways to solve these kind of coefficients. We're saying, like, if it's raining 15 days and snowing 15 days, so it's 15 days rain out of 30, what is the coefficient that's going to go in front? When I do that expansion of r plus s to the 30th power, how many different ways can I make this combination? How many different pathways can I follow on my tree diagram that lead me to the same outcome of 15 R's and 15 S's? Okay, I want to know how many different ways can I get that? How many different ways can I get 20 heads and 10 tails if I flip 30 times? All right, so in our next video, we're going to talk about how we understand combinations and how many different ways there are to do certain things.